In this lecture, we will see how to use Laplace transform to analyze the circuit, or we can also say how to analyze the circuit using Laplace transform in the S domain. S domain is nothing but sequential domain or frequency domain. Okay, so here we have to follow three standard procedures. The first one is replacing each circuit element. For example, if you are given a circuit and perform the analysis by using Laplace transform, then you have to replace each circuit element with its S domain equivalent, and then the initial energy, especially in inductor and capacitor, should be taken into account by adding independent source in series or parallel. It means whenever you have the inductor or capacitor, there is a possibility for those elements may have the initial energy. If there is an initial energy in the inductor or capacitor, then you must consider those values into the account when you solve the problems. That's what the first the step is telling. The second step is then you have to write and solve algebraic equations by the same circuit analysis techniques developed for resistive networks. So maybe you have studied different techniques in circuit theory or networking theory. So you have to use either of the techniques, and you have to write algebraic equations for voltage and current for each loop in the given circuit. And the step 3 is you have to obtain the T domain solutions by inverse Laplace transform. So what does it mean? So first you are converting the circuit into the S domain and writing the equation in S domain, and of course you are performing the Laplace transforms. Then after you complete the Laplace transform, then again you have to convert back into the time domain, because once you perform the Laplace transform of these algebraic equations, then it's in S domain, frequency domain. So but we want the final answer should be in time domain again. So for that you have to perform inverse Laplace transform again. So these three steps are very simple. It may be a little bit difficult to understand what does it mean at this moment, but when we see the example problem, then you will understand very clearly what are these steps are. Okay, so now we will see the problems, how to do the circuit analysis using Laplace transform. Before we go into the problem, I would like to recall again the same information what I have shared with you earlier. So for example, voltage source. So how can you represent the voltage source in time domain? For example, here we are saying here V of t. So we have the polarity plus minus, and this is the notation or the representation of the voltage in the time domain, voltage with respect to time. And if you want to convert this into the Laplace domain or S domain, then you have to write it in a different way. So actually this is a small v of t. So here capital V of S, capital V of S. So the same voltage we are representing in S domain by this notation, capital V of S. The second one is the current source. So the current source we are representing with I of t, small I of t in time domain. The same current you have to represent in a different way in S domain. S domain is capital I of S. And similarly, now we will go to some elements, passive components. So for example, resistor. So now you can see this resistor we are representing like this in the time domain. So we have the polarity plus and minus. It's just same as the source voltage polarity. So here V of t, small v of t is indicating the voltage drop across this resistor, and here the current small I of t is flowing through this resistor. Okay, this is the representation of the resistor in time domain. Now if you want to do the same in S domain. You have to represent the same resistor in S domain. Then how can you do that? You have to draw the same circuit like this, the same resistor you are writing, and the polarity is also the same. So here the voltage drop across the resistor in S domain is capital V of S, and current flowing through this resistor is capital I of S. It's very simple. So for resistors, it's very easy and straightforward. Just we are putting capital V of S and capital I of S instead of T. So this is just following the Ohm's law. It's not something special. So if you want to write the formula for the voltage drop across the resistor, then you can use this V is equal to IR format. So V of t is equal to I of t times R. So it means voltage drop across the resistor in time domain is equal to the current flowing through this resistor small I of t times R. R is the resistor value. So now you can convert the same equation into the S domain in this way. So you already know how to convert the voltage source into S domain, how to convert the current source into the S domain. So here capital V of S is equal to capital I of S times R. So this is the equation in S domain. So now we completed for resistor. Now we will see inductor. Inductor, so you can write the inductor like this. So the inductor polarity is also same as the supply voltage. So plus minus. So here L is the value of the inductor, and this small v of t is the voltage drop across this inductor, and the I of t, the small I of t, is the current flowing through this inductor. Okay, this is the drawing or the representation of the inductor in time domain. Now you have to convert the same into this S domain. So S domain, whenever you convert this inductor from time domain into S domain, you must consider the initial energy of this inductor. That is what I told you just before here. So you have to consider the initial energy of the inductor and capacitor. You must take into account. So you have to consider the initial voltage. So for example, I consider the initial energy as a series source. So here I draw the same inductor, and then I added one more initial source, energy source. Remember, one important thing you have to note down, the inductor polarity is plus minus, and the initial voltage source, the polarity will be the opposite. So now you can have to start from here, plus minus or minus plus. So always the inductor value, the initial energy of the inductor, its polarity is the opposite of the actual inductor polarity or the source voltage polarity. So the polarity is opposite to the overall polarity. There is nothing but the source polarity. And also another point you should note down, the initial voltage due to initial current. Yes, so this is the initial voltage. We know inductor and capacitors, they always store the energy. Inductor is storing the energy. Whenever the current is flowing through the inductor, inductor is storing in terms of EMF, electromagnetic field or electromagnetic force, and the capacitor is also doing the same. So whenever the current is flowing through the capacitor is storing the energy in terms of charges, electrical charges. Okay, so here inductor, so this is the pre-stored energy or the initial energy due to the current. So here we represent this one as a L dot or L times small I of 0 minus. It means 0 is indicating the initial condition. So there is you have to write like this, and then for inductor you have to write S times L. L is the value of the inductor, S is to represent this is in the S domain. So SL here, and here is L times I of 0 minus. So now you know how to write the inductor in the time domain and their label, and also the inductor in the S domain and their label, and the voltage and current. Okay, so now again, voltage across the inductor, so we can write the formula same like the resistor. So here L times d I of t divided by dt. Same Ohm's law. Here also you are using the same. V is equal to IR. Remember, that is the voltage uh, that is the Ohm's law. So here also we are doing the same. V is equal to, here we don't have the resistance, here instead because this inductor, so we have the inductance. So inductance times we have to differentiate the current which is flowing through this inductor. So di of t divided by dt. So L is equal to value of the inductor, derivative of current. Derivative of the current means I of t, we are using the differentiation, right? So that is derivative of the current is flowing through the inductor L. So this is the time domain representation. Now if you talk about the S domain representation, then you have to convert everything into the with respect to S. So capital V of S is equal to SL I of S minus L times I of 0 minus. I of 0 minus L is, this is nothing but the initial source, initial energy source, and this is the actual inductor and its uh, current representation. Okay, so if initial current is equal to 0, if we assume there is no initial energy or initial current in this inductor, we can always ignore this part. So we can keep this L times I of 0 minus is equal to 0. So this second part of the equation will not be available anymore. So now we are using only the first part. So now the equation is same like the Ohm's law. So SL times I of S. So this is the impedance value and this is the current value. Okay, so where SL is equal to impedance of the inductor, which is nothing but the constant. Same here. So I of S times R is the constant value. Here also SL is the constant value. Okay, so this is for inductor. Now we will see one more last element, that is capacitor. So in the capacitor, what is happening? So you are just drawing the capacitor in time domain, and we have the polarity plus and minus. So the C is the value of the capacitance, and V of t is the voltage drop across the capacitor, and I of t is the current is flowing through this capacitor. Okay, so now you can draw the same component or the element in S domain. So you can draw like this, but you have to add the initial source, the initial energy of this element. So I am adding this initial energy. That is the first step we talked about. So here the polarity is same as the source voltage. So plus minus, here also the plus minus. Remember, I also said something called source voltage. So because of course here we have the capacitor voltage. Why I mentioned source voltage? Because when we consider the circuit, if you are given any circuit, definitely you will have some kind of source voltage. Of course you will have the load, you will have the source voltage. So the capacitor polarity will always be, for example, if I have let me just take my pen. So if I have the source here, so maybe here I have the plus minus, and then I am connecting here, and I can connect the load whatever I want here. It can be a resistive load or inductive load or the combination of resistive and inductive load. Okay, so in this kind of situation, what is the source polarity? Plus minus, right? So the same plus minus we are writing here. That is what I mentioned, same as the source polarity. Okay, so right now just to forget about these things. We will see the circuits later to analyze the circuit operation. Now we are seeing only how to represent the capacitor in time domain, how to represent the capacitor in S domain. Okay, so that is our point right now. So now the voltage, now you know this C. So in the S domain, you have to write 1 divided by SC, and the V is nothing but, here is small v of t, here is capital V of S. I think I missed to write this. Yes, this is a capital V of S. Okay, so that is how you have to write. And the constant value is 1 divided by SC. And the initial source is, the polarity is same like the capacitor, but inductor, remember, inductor is the opposite. So inductor, we have the plus minus, but here the polarity for the initial source is minus and plus. Here is the same, plus minus, plus minus. Okay, here the constant is 1 divided by S, and V of 0 minus. The V of 0 minus is indicating the initial condition of this capacitor. and the current is flowing through this capacitor is I of S. So V of S is the voltage drop across the capacitor. I of S is the current is flowing through this capacitor, and this one is indicating the initial source or initial energy of the capacitor. Okay, so that's all. And voltage, now we can also write the formula actually. Voltage across the capacitor is V of t is equal to 1 divided by C integral of minus infinity to t I of t times dt. So now this is the standard formula to calculate the voltage drop or the voltage potential across the capacitor. So this integral is indicating, so we are accumulating all the charges which is stored into this capacitor, capacitor C. So 1 divided by C, that is nothing but the capacitance value. So the integral is always giving the mean value or the average value. So average of all the charges. So the time interval is minus infinity to t, that is the charging time of the capacitor. So now if you want to convert the charge into current, of course we are using this integral. So instead of writing the charge Q, we are writing the current directly because we already put the integral and the limit. So I of t times dt, the derivative. So the reciprocal of C value. So here you can see the reciprocal of C value times current, integral of current flowing through this capacitor, which is giving the voltage drop or the voltage potential across the capacitor. So where 1 divided by C is equal to the constant, so it converts the charge into the voltage. So why we are using integral? I already mentioned that just before. So because the capacitor stores charges Q and we integrate all the charges to produce the current I of t. We integrate all the charges. So remember the key word here, integrate. So how we are integrating? So we have to use the equivalent mathematical operator for the integration to integrate all the charges. So that is why we are using this integral. So this is the mathematical operator. You have already studied about differentiation, integration. So now we are using those differentiation and integrations in practical circuits. How we are using that? So if you wondered why we are using this integral, what is the use of this integral sign? This is the use. Okay, so now this is the time domain representation. Now you have to convert the same equation into the S domain. So now V of t, the small v of t, it will become capital V of S is equal to 1 divided by SC. So in the S domain, we have to write like this: 1 divided by SC, capital I of S, plus the initial source is 1 divided by S times V of 0 minus. So again, if you assume there is no initial voltage, then you can ignore this second part of the equation. Then only you will have this equation. V of S is equal to 1 divided by SC times I of S. So that will look like same like the Ohm's law. So we know V is equal to I times R. That is the Ohm's law, right? So here we have for the capacitor, here we have the I, and instead of R, of course, here we have the capacitance value. So we are using the reciprocal. So 1 divided by SC. SC is indicating the S domain. So 1 divided by SC is the impedance of the capacitor, which is also constant. Okay, so now if you remember this basic thing, for example, like what I said just before, so how can you represent the voltage in time domain and S domain? How can you represent the current source in time domain and S domain? How can you represent the resistors in time domain and S domain and their equations for voltage, and also the same inductor in time domain and S domain and their equations, voltage drop equations in time domain and S domain. And finally, we had seen the capacitor, how to draw the circuit, the element in the time domain and S domain, and its equation in time domain and S domain. So if you know this one clearly, then now we are ready to jump into the problem solving. So one small problem I am asking you now, how to represent this below circuit, this circuit, time domain circuit into Laplace domain. Can you draw this same circuit the time domain circuit into S domain? I had already given the answer here. If you want to solve this, do not look at this answer. Just please stop this for a while and then you try to draw the circuit by yourself and then you can compare with the solution. So I just draw the same. So what you are seeing in this circuit, you are seeing R, L, C. So these three elements are connected in series and this is a closed loop and we have the current. Current is flowing into this loop I of t. Okay, so this is R, capital R. We are not, this is the S domain representation of the same circuit. So resistor has no change. So R as it is. So we are writing the inductor. I am drawing the same like here. The S domain is also the same, but I am adding the initial source of the inductor. So inductor is same as the source. Now, if you consider this capacitor as the source, then the plus minus, the same here also will appear. I can take the pen. The resistor, I think I missed to put the polarity. So this is plus and minus, same as the supply. And here also we have the plus and minus, but the initial voltage is the opposite polarity. So minus and plus. And this is I0 minus, I of 0 minus times S. This is indicating the initial source of this inductor. And the capacitor is also the same. So the capacitor we have, and I am just adding only the initial source, V of 0 minus divided by S. Here I wrote the equation with respect to current in the inductor, and here in this capacitor the initial voltage, the initial value I am writing with respect to voltage. So V of 0 minus divided by S. Here is I of 0 minus times S. So I am writing the initial source of the inductor with respect to current. So here I told you inductor is storing in terms of EMF, capacitor is storing in terms of charges. Okay, so that's all. So now you know this. So V of 0 minus divided by S, it's indicating the initial source voltage of this capacitor, and the capacitor, the constant is 1 divided by SC. So what you have to remember here is R is just R as it is. The inductor value is always multiplied by S. So L times S or SL, and the capacitor is always SC, yes, the same like here, but it's a reciprocal. So 1 divided by SC. So that is the difference between inductor and capacitor. And the initial source, you can write it either in terms of voltage or current in both cases. So now I used the RLC like this. Instead, in the problem, if you are given the values, for example, the resistor can be any value. In this example, the 2 ohms, and you have the inductor. Maybe it can be 1 Henry, and capacitor can be 1 divided by 2 farad or 0.5 farad. So now you can draw the same circuit. Now I have the circuit, RLC series circuit. So please draw the circuit again in time domain and also S domain. Instead of using the RLC, you use the particular value. Now this is the just a variable. Instead of this, you just write, you apply the values and draw the same circuit. This is just a small task for you. If you are done this, then we are done with this lecture and we will go and solve the problems in the next lecture. Thank you.